Hi everyone, my name is Stefano and today I'll be presenting on emerging battery technologies with a focus on magnesium ion batteries. As many of us know, batteries have become one of the most important technologies in today's world. They power everything from our smartphones and laptops to electric vehicles and renewable energy storage systems. Most of these applications currently rely on lithium-ion batteries because they provide high energy density and good performance. However, lithium-ion batteries also have several limitations, including cost, safety concerns, and the limited availability of some raw materials. Because of these challenges, researchers have been investigating alternative battery chemistries that could become the next generation of rechargeable batteries. One of the most promising alternatives is the magnesium ion battery, which is the technology I will be discussing today. During this presentation, I will explain how magnesium ion batteries work, why engineers are interested in them, their advantages and disadvantages, the challenges that still exist, and what their future might look like. Before getting into the technical details, I would like to briefly explain how this presentation is organized. I will begin with a short introduction explaining why magnesium ion batteries are currently receiving so much attention. Then I will discuss the history behind their development and how researchers have improved the technology over time. After that, I will explain the battery architecture and the working principle, including how magnesium ions move inside the battery during charging and discharging. Next, I will discuss the materials used inside the battery and explain the chemistry that allows electrical energy to be stored. I will also introduce several engineering equations that are commonly used to analyze battery performance, including Faraday's law, specific capacity, battery energy, and the Nernst equation. Later in the presentation, I will evaluate the battery's performance, compare it with lithium-ion batteries, discuss its advantages and limitations, and finally examine current research, commercialization, environmental impacts, and future applications. By the end of this presentation, I hope you will have a clear understanding of why magnesium-ion batteries are considered one of the most exciting emerging battery technologies. Introduction. Let's begin by answering a simple question. Why are researchers even looking for alternative to lithium-ion batteries? Although lithium-ion batteries have transformed portable electronics and electric vehicles, they are not perfect. One of their biggest challenges is safety. Under certain conditions, lithium-ion batteries can overheat and experience what is known as thermal runaway. During thermal runaway, the battery temperature increases rapidly, sometimes causing fires or explosions. This is one reason why damaged electric vehicle batteries or defective phone batteries occasionally appear in the news. Another challenge involves raw materials. Lithium, cobalt, and nickel are not evenly distributed around the world. Mining these materials can be expensive, environmentally challenging, and sometimes create supply chain risks because production is concentrated in only a few countries. As global demand for electric vehicles continues to increase, these concerns become even more important. This is where magnesium becomes very attractive. Magnesium is actually the eighth most abundant element in the Earth's crust, making it much more available than lithium. It can also be extracted from seawater, giving it an enormous potential supply. Another major advantage is safety. Unlike lithium metal, magnesium metal is much more less likely to form structures called dendrites. Dendrites are tiny needle-like metal structures that can grow during charging. If these dendrites become large enough, they can puncture the separator inside the battery and create an internal short circuit. Since magnesium naturally suppresses dendrite formation, Much more better than lithium, researchers believe magnesium batteries could eventually become safer rechargeable batteries. In addition to safety, magnesium also offers excellent volumetric capacity. Each magnesium atom releases two electrons while lithium only releases one. That means magnesium can theoretically store more charge within the same physical volume. Because of these advantages, including abundance, safety, sustainability, and high theoretical capacity, magnesium-ion batteries have become an important area of battery research around the world. Historical background. Now let's look at how magnesium batteries develop over time. Although lithium-ion batteries became commercially successful during the early 1990s, scientists had already begun exploring magnesium batteries around the same period. The original idea seemed very promising because magnesium offers several theoretical advantages over lithium. However, researchers quickly encountered a major obstacle. The problem wasn't the magnesium metal itself. The biggest challenge was finding an electrolyte that actually worked. An electrolyte must allow magnesium ions to move freely between the electrodes while remaining chemically stable. Unfortunately, many early electrolytes reacted with the magnesium metal surface. Instead of allowing ions to move normally, they form a passivation layer that blocks further electrochemical reactions. This essentially stopped the battery from functioning correctly. For many years, this prevented rechargeable magnesium batteries from becoming practical. During the years 2000s and 2010s, scientists made significant progress. New electrolyte formulations were developed that allow magnesium to repeatedly plate and strip during charging and discharging. Researchers also began discovering better cathode materials capable of accepting magnesium ions. Materials containing vanadium, sulfur, and transition metals oxides show encouraging performance. As computational modeling improved, researchers were also able to predict which crystal structures might allow magnesium ions to diffuse more easily. Today, magnesium-ion batteries remain largely in the research stage. Universities, national labs, and private companies continue improving every component of the battery. While we still don't see magnesium-ion batteries in commercial electric vehicles or consumer electronics, the amount of published research has increased dramatically over the last decade. Many experts believe magnesium batteries could eventually become an important complement to lithium-ion technology. Battery architecture. Now let's examine the basic structure of a magnesium-ion battery. Like most rechargeable batteries, magnesium-ion batteries contain several components that work together to produce electricity. The first component is the anode. The anode is typically made from magnesium metal. During discharge, magnesium atoms lose electrons and become magnesium ions. These ions leave the anode and begin moving through the battery. The second component is the cathode. The cathode acts as the storage location for magnesium ions during discharge. Researchers continue developing new cathode materials because one of the biggest challenges is finding materials that allow magnesium ions to move quickly. The next component is the electrolyte. The electrolyte is not an electronic conductor. Instead, it conducts magnesium ions between the two electrodes. Choosing the correct electrolyte is extremely important because it directly affects battery performance, efficiency, stability, and lifespan. Another important component is the separator. The separator is a thin, porous membrane placed between the anode and the cathode. Its purpose is to prevent the electrodes from touching each other, which will create a short circuit. Even though it blocks electrical contact, its tiny pores still allow magnesium ions to travel through the electrolyte. Finally, we have the current collectors. These are metallic sheets attached to each electrode. Their job is to carry electrons into and out of the battery throughout the external circuit. Copper is commonly used on the anode side, while aluminum is frequently used for the cathode. When all these components work together, the battery is able to convert chemical energy into electrical energy that can power external devices. Now that we have looked at the physical structure of the battery, the next question is how all of these components actually work together during charging and discharging. In the next section, I will explain the complete working principle of a magnesium ion battery and describe exactly how magnesium ions and electrons move throughout the system. Like every rechargeable battery, a magnesium ion battery converts chemical energy into electrical energy through electrochemical reactions. We'll start with the discharge process, and this is when the battery is powering a device. Inside the anode, magnesium exists as a solid metal. During discharge, each magnesium atom loses 2 electrons through an oxidation reaction. As the magnesium atom loses these electrons, it becomes a positively charged magnesium ion, or Mg2+. This is an important point because magnesium releases 2 electrons per atom, while lithium only releases 1. This gives magnesium a very high theoretical charge capacity. Once the electrons are released, they cannot travel through the electrolyte because the electrolyte only conducts ions. Instead, the electrons travel through the external circuit. If the battery is connected to a phone, laptop, electric vehicle, or another device, those electrons flow through the device and provide electrical power before returning to the battery. At the same time, the magnesium ions travel through the electrolyte toward the cathode. The separator allows these ions to pass while preventing the electrodes from touching each other. When the magnesium ions reach the cathode, they enter the cathode material through a process called intercalation. Intercalation simply means that the magnesium ions insert themselves into the crystal structure of the cathode without completely changing its overall structure. You can imagine it like placing books onto empty shelves in a bookshelf. The bookshelf stays the same, but the books move in and out. During charging, everything happens in reverse. An external power source forces electrons back toward the magnesium electrode. At the same time, magnesium ions leave the cathode, travel back through the electrolyte, and are deposited again as a magnesium metal on the anode. This charging and discharging processes is what allows rechargeable batteries to be used hundreds or even thousands of times. However, one of the biggest engineering challenges is that magnesium ions move much more slowly than lithium ions because magnesium carries twice the electrical charge. That stronger attraction to surrounding atoms makes diffusion inside the cathode much more difficult. This slow diffusion is one of the main reasons magnesium ion batteries are still under development. Materials and chemistry. Now let's take a closer look at how materials are used inside the battery. Each component has a specific job, and choosing the right material has a major effect on the performance. Let's begin with the anode. Anode is usually made from pure magnesium metal. This is one of the largest advantages of magnesium ion batteries because the battery can directly use magnesium as the negative electrode. Magnesium metal is very inexpensive, naturally abundant, and provides high volumetric capacity. Next is the cathode. Unlike lithium-ion batteries, there is currently no perfect cathode material for magnesium batteries. Researchers have tested many different materials. Some of the most common include transition metal oxides, transition metal sulfides, vanadium oxides, manganese compounds, and sulfur-based cathodes. Each material has its advantages and limitations. Some store large amounts of magnesium but have poor cycle life. Others provide good stability but lower energy density. Finding the ideal cathode continues to be one of the biggest research challenges. The electrolyte is equally important. Its job is to transport magnesium ions between the electrodes. Unlike water-based electrolytes, magnesium batteries usually use non-aqueous electrolytes because water reacts too easily with magnesium metal. Scientists continue developing new electrolyte formulations that improve conductivity while preventing unwanted chemical reactions. The separator is normally a thin polymer membrane containing microscopic pores. Although it physically separates the electrodes, it allows magnesium ions to pass through with minimal resistance. Finally, the current collectors provide electrical pathways for the electrons. Copper is commonly used on the anode side while aluminum is typically used for the cathode. Overall, every material inside the battery must work together. Even if one component performs poorly, the overall battery performance decreases significantly. Let's now examine the electrochemical reactions taking place inside the battery. The first reaction occurs at the magnesium anode. During discharge, magnesium atoms are oxidized. The reaction can be written as magnesium becoming magnesium ions plus 2 electrons. This reaction is called oxidation because the magnesium loses electrons. Those released electrons then travel through the external electrical circuit. Meanwhile, the magnesium ions move through the electrolyte toward the cathode. At the cathode, a reduction reaction takes place. The incoming magnesium ions combine with the electrons arriving from the external circuit. The exact chemical reaction depends on which cathode material is being used. Most experimental magnesium batteries rely on intercalation reactions. Intercalation basically means that magnesium ions enter the spaces within the crystal lattice of the cathode. The crystal structure remains mostly intact while storing the ions. Some battery chemistries instead rely on conversion reactions. During a conversion reaction, the cathode material changes into entirely different chemical compounds. These reactions can sometimes provide higher capacities, but they usually involve large volume changes and reduced cycle life. For a rechargeable battery, these reactions must remain irreversible. If the reactions become irreversible, the battery permanently loses capacity and eventually fails. This is one of the many reasons why researchers spend so much time studying electrode chemistry. Improving the reversibility of these reactions directly increases the battery's lifespan. Now let's connect the battery technology to engineering principles. Faraday's law, Faraday's law relates the number of electrons transferred to the total electrical charge. As we can see on the right, that's the equation for Faraday's law. Next, we have the specific capacity, which basically measures how much charge a material can store per gram. We also have the equation on the right side. Then we have battery energy, which calculates the energy stored using voltage and charge. And finally, we have the Nernst equation, which basically explains why the battery voltage changes as the chemical reaction progresses. Now let's evaluate how magnesium ion batteries perform today. The first metric is energy density. Energy density tells us how much energy a battery stores relative to its size or weight. The next metric is power density, which measures how quickly energy can be delivered. Another important measurement is cycle life. Cycle life represents the number of charge and discharge cycles a battery can complete before its capacity significantly decreases. Another important measurement is Coulombic efficiency. Coulombic efficiency compares the amount of charge recovered during discharge to the amount originally supplied during charging. And finally, engineers evaluate round-trip efficiency. This measures how much energy can actually be recovered after charging and discharging. Now that we have discussed how magnesium-ion batteries work, let's compare them with today's dominant battery technology, which is lithium-ion battery. As we can see here, we have a table showing each property comparing magnesium ions and lithium ions. We have charge, carrier, electrons per ion, energy density, power density, cycle life, Coulombic efficiency, safety, raw material, material cost, and commercial status. So here we can see basically the comparison between magnesium and lithium ion. Now let's talk about some advantages. Some of the advantages are high natural abundance, lower material cost, improved safety, high volumetric capacity, and finally, is environmentally friendly. Some of the limitations we have are a slow Mg2 plus ion diffusion, limited cathode materials, electrolyte compatibility issues, lower operating voltage, and finally, there is a limited commercialization for these batteries. Commercialization. To become commercially successful, magnesium-ion batteries must demonstrate competitive energy density, long cycle life, fast charging, low manufacturing cost, and reliable long-term performance. Many experts believe the first commercial applications will probably be in grid energy storage. Unlike electric vehicles, stationary storage systems are less sensitive to battery weight. Instead, safety, long life, and low cost become much more important. If magnesium batteries prove to be successful in stationary energy storage, future improvements could eventually allow expansion into transportation as well as portable electronics. Current research. The final topic in this section is current research. Today, battery scientists around the world are working on solving the remaining technical challenges. One major research area is advanced cathode materials. Researchers continue searching for materials that allow magnesium ions to move more easily throughout the crystal structure. Another important area is electrolyte development. Experts are creating new electrolytes that improve conductivity while preventing unwanted chemical reactions with magnesium metal. Other thing that is being studied right now is interface engineering. The interface between the electrode and electrolyte is where electrochemical reactions actually occur. Finally, computational modeling and artificial intelligence are becoming valuable tools. Instead of testing thousands of materials experimentally, researchers can now use computer simulations to predict which materials are most likely to succeed. This significantly reduces development time and research costs. Overall, magnesium-ion battery research is advancing rapidly. Now let's talk about the environmental impact. As the world continues transitioning toward renewable energy and electrical transportation, sustainability has become just as important as battery performance. One of the biggest advantages of magnesium-ion batteries is that magnesium is an extremely abundant natural resource. Another environmental advantage is the reduced dependence on critical minerals. Many current lithium-ion batteries require cobalt and nickel. Mining these materials can have significant environmental impacts. Also, there is a lower supply chain risk. There are currently recycling methods under development. And finally, there is potential for more sustainable batteries. Future outlook. There is continued improvements in battery materials. There is potential for grid-scale energy storage. There is future use in electric vehicles. Also, these batteries will become safer alternative to lithium-ion batteries and likely to complement and maybe not replace lithium ions. Conclusions. Promising alternative to lithium-ion batteries. Magnesium-ion batteries are becoming a promising alternative to replace to eventually replace lithium-ion batteries. They are safer and more sustainable battery chemistry. There are still some technical challenges to be solved. Commercialization is still in the research stage, and there is a strong potential for future energy storage applications. And finally, here are the references that I use for this presentation. Thank you.